Welcome to my sleep science channel. Before we begin tonight's journey, take a moment to like the video, subscribe to the channel, and tell me in the comments where you are watching from. As you settle in and relax, allow your thoughts to drift across the vast reaches of space toward the enormous cosmic neighborhood that has been our home for billions of years. The solar system is such a familiar part of our lives that it can be easy to forget how extraordinary it really is. Every morning, sunlight reaches Earth after traveling across nearly 150 million kilometers of empty space. The warmth on your skin, the light that enters your window, and the energy that powers nearly all life on our planet all come from a single star at the center of a vast gravitational family. That star is the Sun, and around it travels a remarkable collection of worlds, moons, asteroids, comets, dust, and invisible fields of energy that together form what we call the solar system. If you could leave Earth and travel outward, the first thing you might notice is how empty space appears. Popular illustrations often show planets lined up neatly beside one another. But reality is very different. The distances between worlds are immense. Earth and the Moon seem closely connected, yet even that relatively short journey would require crossing hundreds of thousands of kilometers of space. Beyond Earth lies Mars, then the giant planets, each separated by distances so vast that ordinary human experience offers almost no comparison. At the center of everything sits the Sun. It contains more than 99% of all the mass in the solar system. In many ways, the Sun is the solar system. Its gravity controls the motions of the planets. Its light illuminates them, and its energy influences nearly every process that occurs throughout this cosmic neighborhood. Without the Sun, the planets would simply drift away into the darkness of interstellar space. Orbiting the Sun are 8 major planets. Closest to the Sun is Mercury, a small rocky world marked by ancient craters and extreme temperature changes. Next comes Venus, hidden beneath thick clouds and possessing a surface hot enough to melt lead. Third is Earth, the only known world where life exists. Then comes Mars, a cold desert planet that still preserves evidence of rivers and lakes from a distant past. Farther outward are the giant planets. Jupiter dominates this region. It is so massive that more than 1,000 Earths could fit inside it. Saturn follows, surrounded by magnificent rings made of countless particles of ice and rock. Beyond Saturn lie Uranus and Neptune, distant worlds of ice, gas, and powerful winds that circle the Sun in regions where sunlight is far weaker than what we experience on Earth. The planets are only part of the story. Hundreds of moons travel around these worlds. Some are larger than entire planets elsewhere in the universe. Beneath icy surfaces, hidden oceans may exist. Volcanoes erupt on distant moons. Frozen landscapes stretch across regions untouched by human footsteps. Every moon has its own history, its own geology, and its own place in the larger story of solar system formation. Between Mars and Jupiter lies the asteroid belt, a region filled with rocky remnants from the early days of planetary construction. Far beyond Neptune stretches the Kuiper belt, a vast population of icy objects left over from the solar system's youth. Even farther still lies a mysterious realm that may contain trillions of frozen bodies, slowly orbiting the Sun at distances almost impossible to imagine. What makes the solar system especially fascinating is that it was not always organized in the way we see today. 4.5 billion years ago, none of these planets existed. There was no Earth, no moon, no oceans, no mountains, and no living creatures gazing up at the stars. The solar system began as something entirely different, a giant cloud of gas and dust drifting through a region of the Milky Way galaxy. Everything around us can trace its origins back to that ancient cloud. The iron in your blood, the calcium in your bones, the oxygen you breathe, and the silicon found in rocks and sand all participated in a story that began long before Earth existed. The materials that make up our world were once scattered across space, mixed together with countless microscopic particles floating through a cold and silent cosmic environment. As we look at the solar system today, we are really looking at the final result of an unimaginably long process. Every planet, moon, asteroid, and comet carries clues about events that occurred billions of years ago. The arrangement of the planets, their compositions, their motions, and even their imperfections all preserve evidence of their origins. The solar system is like a gigantic historical record written across space itself. Tonight, as you imagine the planets quietly circling the sun, it is worth remembering that this calm appearance hides a dramatic past. The peaceful solar system we know today emerged from powerful forces, enormous collisions, intense heat, and vast clouds of material slowly transforming under the influence of gravity. The story begins not with planets, but with darkness, dust, and a cloud so enormous that it would eventually give birth to everything we know. Long before Earth existed, before oceans formed, before mountains rose from the surface of any planet, and before the sun shone across the darkness of space, there was an enormous cloud drifting quietly through a distant region of the Milky Way galaxy. This cloud did not resemble anything familiar from everyday life. It was not a fluffy white cloud like those floating above Earth. Instead, it was a vast collection of gas and dust stretching across distances so large that entire solar systems could fit inside it many times over. To understand how our solar system formed, it helps to imagine the Milky Way not as a collection of isolated stars, but as a living environment where stars are constantly being born, evolving, and eventually dying. Throughout the galaxy, giant clouds of gas drift between the stars. Astronomers call these molecular clouds because many of the atoms inside them combine to form simple molecules. These clouds are among the coldest places in the galaxy. Temperatures can fall so low that ordinary human experience offers no meaningful comparison. Inside these clouds, darkness dominates. The gas is thin by Earth standards, yet when spread across such enormous distances, it becomes dense enough to block starlight. If you could somehow travel into one of these regions, you would find yourself surrounded by darkness unlike anything seen on Earth. Even the brightest stars would disappear behind curtains of dust. The cloud would feel silent and motionless, though deep within it, subtle processes would already be shaping the future. Most of the material in these clouds is hydrogen, the simplest and most abundant element in the universe. Hydrogen formed shortly after the birth of the cosmos itself. Mixed with it are smaller amounts of helium and traces of heavier elements such as carbon, oxygen, silicon, magnesium, and iron. These heavier elements have a remarkable history. They were not present at the beginning of the universe. Instead, they were forged inside ancient stars that lived and died long before our sun appeared. In a sense, the cloud that eventually produced our solar system was already carrying the legacy of previous generations of stars. Somewhere in the distant past, massive stars had burned through their nuclear fuel. Some expanded into giant red stars. Others ended their lives in powerful explosions that scattered newly created elements across the galaxy. Those materials drifted through space for millions of years, eventually becoming part of the giant cloud from which our sun and planets would emerge. The cloud was not perfectly uniform. Some regions contained slightly more material than others. These differences may have been tiny, almost impossible to detect, but over vast periods of time they became important. Gravity was quietly at work everywhere. Every particle exerted a small gravitational pull on every other particle. Although these forces were weak, they never completely disappeared. Imagine a calm lake on a windless evening. At first glance, the surface may seem perfectly still, yet small ripples continue to move beneath the surface. Molecular clouds behave somewhat similarly. Even when they appear peaceful, they contain currents, turbulence, and slow motions occurring across enormous distances. Material drifts from one region to another. Some areas become denser while others become thinner. As millions of years passed, one particular region within this giant cloud began gathering slightly more material than its surroundings. Gravity slowly strengthened there. More gas drifted inward. More dust accumulated. The denser the region became, the stronger its gravitational attraction grew. This process was incredibly slow by human standards, but in the grand timescales of the galaxy, it was part of a natural cycle, repeated countless times. The cloud itself was enormous. If our entire solar system had existed within it at that time, it would have occupied only a tiny fraction of the cloud's total volume. The future Sun, Earth, Jupiter, Saturn, and every other object that would eventually form were all mixed together as scattered particles. There were no planets, no moons, and no clear boundaries separating one future world from another. Everything existed as part of a single diffuse environment. Dust grains floating within the cloud played an important role. Though tiny, these particles consisted of minerals, metals, and complex compounds that would later become the building blocks of planets. Some grains were smaller than smoke particles. Others contained frozen layers of water, methane, ammonia, and other substances. Over time, countless collisions caused these particles to interact, cluster, and drift through the cloud. If you could observe the region over millions of years in a time lapse, you would notice subtle changes. The cloud would not remain static. Denser knots would emerge. Streams of material would flow inward. Gravity would gradually transform a loose collection of gas and dust into something more concentrated. The process would still appear gentle and quiet, yet the foundations of a future solar system would be taking shape. One of the most fascinating aspects of this stage is how ordinary the cloud initially seemed. There was nothing visibly special about it. Similar clouds exist throughout the Milky Way even today. Many contain the raw ingredients needed to produce future stars and planets. Somewhere within those distant regions, entirely new solar systems may currently be beginning their own journeys. The future Earth existed only as scattered atoms drifting through darkness. The water that would one day fill oceans floated as individual molecules. The iron destined for mountain ranges, cities, and living organisms drifted among countless other particles. Nothing yet resembled a world. Nothing hinted at continents, forests, or life. Yet all the ingredients were already present. As the dense region continued gathering material, gravity slowly gained control. The balance that had existed for millions of years was beginning to change. The cloud could no longer remain exactly as it was. A threshold was approaching, a moment when the inward pull of gravity would begin to overwhelm the forces resisting collapse. The long, quiet age of the cloud was gradually coming to an end, and one of the most important transformations in cosmic history was about to begin. As the giant cloud that would eventually form our solar system drifted through the Milky Way, it contained far more than simple hydrogen gas. Hidden among its particles was a rich collection of elements that had been manufactured during events that occurred long before the sun existed. Every rocky planet, every moon, every asteroid, and every living thing on Earth owes its existence to these ancient materials. The story of our solar system is not only the story of the sun and planets, it is also the story of cosmic recycling on a galactic scale. If someone could travel backward in time to the earliest moments of the universe, they would find a cosmos containing very few types of atoms. Hydrogen dominated almost everything. Helium was present as well, along with tiny traces of a few other light elements. The heavier elements that make up modern planets did not yet exist. There was no iron, no oxygen, no silicon, no carbon-rich dust drifting through space. The universe was far simpler than it is today. The first stars changed everything. These early stars formed from vast clouds of hydrogen and helium. Deep within their cores, temperatures and pressures became enormous. Under such extreme conditions, atomic nuclei began to combine. Hydrogen was transformed into helium. As stars aged, more complex reactions created heavier elements. Over millions of years, stars became giant cosmic factories, slowly manufacturing the building blocks that would later shape entire worlds. Some stars were much larger than our sun. Massive stars lived shorter lives but produced greater quantities of heavy elements. Their interiors became layered structures. Different regions inside the star created different materials. Carbon formed in one layer. Oxygen appeared in another. Silicon accumulated deeper inside. Eventually, iron began to collect near the center. Iron represented an important turning point. Unlike earlier fusion reactions, creating elements heavier than iron no longer provided energy to support the star. Once enough iron accumulated, the delicate balance inside the massive star began to fail. Gravity gained the upper hand. The star's core collapsed, and one of the most powerful events in the universe occurred. A supernova explosion erupted. For a brief period, a single dying star could outshine billions of other stars. Vast quantities of matter were blasted outward at incredible speeds. Elements forged over millions of years were scattered into interstellar space. The explosion itself also created additional heavy elements that could not easily form inside ordinary stars. Gold, silver, uranium, and many other rare materials were produced during these violent moments. The debris expanded outward for thousands of years. Eventually, it mixed with nearby gas clouds. Material from many generations of stars accumulated together. Ancient stellar remains blended into enormous molecular clouds that drifted through the galaxy. One of these clouds would eventually become the birthplace of our solar system. This means that every atom of calcium in your bones was once part of a star. The oxygen you breathe was forged inside a stellar furnace. The iron carried through your bloodstream originated in an ancient star that died billions of years before Earth existed. The carbon that forms the basis of life was created long before our planet appeared. When astronomers say that humans are made of stardust, they are not speaking poetically. They are describing a literal physical reality. Within the cloud that would eventually form the solar system, tiny grains of dust floated among vast quantities of gas. These grains were extremely small. Many were smaller than particles of smoke. Yet despite their size, they were enormously important. They contained silicates, metals, carbon compounds, and frozen materials that would later become part of planets. If you could observe one of these microscopic dust grains, it might not seem impressive. Yet billions upon billions of such particles filled the cloud. Together, they represented the raw ingredients from which mountains, continents, planetary cores, and moons would eventually emerge. Some particles carried frozen water, others contained frozen methane, ammonia, and carbon dioxide. In the coldest regions of the cloud, ice could accumulate around dust grains like thin coatings. These icy coatings often helped particles stick together when they collided. Although this process was still far in the future, the foundations for planetary construction were already present. The cloud itself was chemically diverse. Different regions contained slightly different concentrations of materials. Temperatures varied. Densities varied. Radiation from nearby stars influenced some areas more than others. All these subtle differences would eventually help determine which materials became part of rocky planets and which became part of giant gas worlds. As millions of years passed, countless dust grains drifted through the cloud. They collided gently. Sometimes they bounced apart. Sometimes they stuck together. Tiny clusters formed and broke apart repeatedly. The process seemed insignificant, but over enormous spans of time, these interactions slowly changed the cloud's structure. The future Earth existed only as scattered ingredients. The future moon was mixed throughout the cloud. The iron that would one day sink into Earth's core floated freely through space. The water destined for oceans and rivers existed as isolated molecules drifting in darkness. Nothing yet resembled a planet, but the ingredients were gathering. One of the remarkable aspects of this stage is how ordinary it appeared. There were no bright planets shining in space. There were no spectacular rings or recognizable worlds. The cloud looked quiet and uneventful, yet within it lay everything necessary to create an entire planetary system. The materials that would eventually become Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and countless smaller bodies were already present. They simply had not yet found their final forms. Like pieces of an enormous puzzle scattered across a vast table, the ingredients waited for gravity to begin organizing them into something new. Slowly, almost imperceptibly, gravity continued strengthening within the densest regions of the cloud. More material drifted inward. More gas accumulated. More dust gathered together. The balance between gravity and the cloud's internal support was beginning to shift. The quiet age of drifting stardust was approaching its end, and the immense cloud that held the ingredients of future worlds was preparing for a dramatic transformation. Before we begin tonight's journey through the origins of our solar system, take a moment to like the video, subscribe to Sleep Science, and tell me where you're watching from. Around 4.6 billion years ago, a region within a giant molecular cloud began to experience a subtle but important change. For millions of years, gravity had been quietly gathering material into denser pockets, but now one of those regions was approaching a critical threshold. The balance that had existed for ages was starting to break down. The cloud was unimaginably large. It contained enough gas and dust to create not only a star, but an entire family of planets, moons, asteroids, and comets. Although the cloud appeared calm from a distance, countless particles were constantly moving. Gas drifted through the darkness. Dust grains collided and separated. Weak magnetic fields threaded through the material. Small disturbances rippled across vast distances. Most of these motions accomplished very little, but gravity never stopped working. Every atom inside the cloud exerted a tiny gravitational pull on every other atom. Individually, these forces were insignificant. Collectively, they were powerful enough to reshape entire regions of space. As matter accumulated within the densest area of the cloud, gravity became stronger. Stronger gravity attracted more matter. More matter increased the gravitational pull even further. A slow cycle began to accelerate. At first, the collapse proceeded almost invisibly. If a human observer could watch the process unfold in real time, nothing would seem to happen. Years would pass. Centuries would pass. Even thousands of years might reveal little obvious change. Yet over hundreds of thousands of years, the transformation became impossible to ignore. The dense region was shrinking. Material was moving inward. The cloud was no longer maintaining its previous structure. As gravity pulled matter toward the center, another important effect appeared. The cloud began to rotate more rapidly. Even a very slow initial rotation became significant as the cloud contracted. This is similar to what happens when a figure skater pulls their arms inward and spins faster. The shrinking cloud conserved its angular momentum, causing its rotation speed to increase. The increasing rotation prevented material from falling directly into the center. Instead, the collapsing cloud gradually flattened. What had once been a roughly spherical region slowly transformed into a rotating disk. At the center, matter accumulated into an increasingly dense object that would eventually become the sun. Surrounding it was a broad disk of gas and dust, extending across billions of kilometers. This disk would become the construction site of the solar system. The center of the collapsing cloud grew hotter as more material fell inward. Gravitational energy was converted into heat. Temperatures rose steadily. The growing concentration of matter compressed itself under its own weight. Pressure increased. The environment became increasingly energetic. While the outer regions of the disk remained relatively cool, the central region was evolving into something very different. Dust grains throughout the disk continued drifting and colliding. Some vaporized in the hotter inner regions. Others survived in cooler areas farther from the center. Different materials behave differently, depending on their distance from the growing proto-sun. This temperature gradient would eventually play a major role in determining which planets formed where. Closer to the center, only materials with high melting points could remain solid. Metals and rocky minerals survived. Water ice could not. Farther away, temperatures dropped enough for ice to exist. This created a much larger supply of solid material in the outer regions of the disk. The consequences of this difference would shape the entire architecture of the solar system. Meanwhile, the collapsing cloud continued feeding material into the central object. The future sun was still not a true star. Nuclear fusion had not yet begun. Nevertheless, it was already becoming the dominant object in the system. Its gravity influenced the motions of surrounding gas and dust. The young solar system was beginning to take on a recognizable structure, even though no planets yet existed. The collapse of the solar nebula was not a sudden event. It was a long, gradual transformation that unfolded over immense spans of time. Yet it represented one of the most important turning points in the history of our cosmic neighborhood. A drifting cloud of gas and dust was becoming an organized system with a central star and a surrounding disk. The ingredients that had once been scattered across a vast region of space were now being gathered into a framework capable of producing worlds. The solar system we know today, with its planets, moons, rings, asteroids, and comets, traces its origins to this remarkable period. Everything that would eventually become Earth, every drop of ocean water, every mountain, every living organism, and every human being was now part of a rotating disk surrounding a growing young sun. The age of planetary construction was drawing closer, and the first foundations of a new solar system had finally been laid. At this stage, the young sun did not resemble the stable star we know today. It was what astronomers call a protostar, a growing object still gathering material from its surroundings. Vast streams of gas spiraled inward from the disk, adding mass to the central body. Every new particle that fell toward the center carried energy. As gravity compressed the growing protostar, temperatures and pressures steadily increased. The process was surprisingly violent, despite taking place over hundreds of thousands of years. The protostar was surrounded by swirling gas moving at tremendous speeds. Powerful magnetic fields twisted through the material. Jets of matter erupted from the polar regions and shot outward into space. From a distance, the scene would have appeared spectacular. Bright streams of glowing gas stretched across enormous distances, while the young star continued feeding on the surrounding cloud. As the protostar accumulated more mass, its interior became hotter. Gravity compressed the gas more tightly with each passing era. Deep within the center, temperatures climbed into the millions of degrees. The pressure became almost unimaginable. Conditions were approaching the threshold required for one of the most important processes in the universe: nuclear fusion. Fusion is the process that powers stars. Under extreme temperature and pressure, hydrogen nuclei move so rapidly that they can overcome their natural electrical repulsion and combine. When this happens, a small amount of mass is converted into energy. The result is an enormous release of power. This energy is what makes stars shine for billions of years. Eventually, the center of the protostar became hot enough for the first fusion reactions to occur. Hydrogen nuclei began combining into helium. Energy flooded outward from the core. The balance of forces inside the object changed dramatically. For millions of years, gravity had been winning the struggle, pulling material inward and compressing the growing star. Now a new force entered the contest. The outward pressure generated by fusion began pushing against gravity. A balance emerged. Gravity continued, pulling inward, while energy from fusion pushed outward. Neither side completely dominated. The result was a stable star. The sun had officially been born. This moment was one of the most important events in the history of our solar system. Without it, there would be no planets as we know them, no oceans, no atmosphere, no life. The birth of the sun transformed the environment of the entire surrounding disk. The young sun was far more active than the modern sun. It rotated more rapidly and produced powerful bursts of radiation. Intense streams of charged particles flowed outward in every direction. These solar winds swept through the disk, interacting with gas and dust throughout the system. The sun was not simply sitting at the center of the disk. It was actively shaping the environment around it. Its light illuminated regions that had previously been dark. Its heat affected temperatures throughout the disk. Materials that could remain solid in the colder outer regions melted or vaporized closer to the sun. This created distinct zones within the protoplanetary disk. Different types of matter accumulated in different locations. Near the sun, temperatures were extremely high. Water ice could not survive. Many volatile substances remained gaseous. Rocky minerals and metals dominated the available solid material. Farther from the sun, temperatures dropped significantly. Water ice became stable. Frozen methane and ammonia could exist. These colder regions contained far greater quantities of solid matter, an advantage that would later help produce giant planets. The newborn sun also inherited most of the mass from the original cloud. Although the surrounding disk appeared enormous, it contained only a small fraction of the system's total material. More than 99% of the mass was concentrated in the central star. This is still true today. The sun remains overwhelmingly dominant compared to everything else in the solar system combined. If someone could have observed the system during this era, they would not have seen recognizable planets. Instead, they would have witnessed a brilliant young star surrounded by a vast disk of gas and dust, stretching billions of kilometers into space. The future Earth existed only as microscopic particles, orbiting within this disk. Jupiter had not formed. Saturn did not yet exist. The moon was nowhere to be seen. The ingredients were present, but the worlds themselves had not yet emerged. Yet, the structure of the future solar system was becoming increasingly clear. A central star now occupied the middle of the system. Around it rotated a flattened disk, rich with raw materials. The conditions required for planet formation had finally been established. The birth of the sun marked the end of one chapter and the beginning of another. For millions of years, gravity had focused on creating a star. Now the attention of the solar system shifted toward a new challenge. Within the rotating disk, countless dust grains continued colliding, sticking together and slowly growing. Tiny particles were beginning a journey that would eventually lead to mountains, continents, oceans, and worlds. The young sun illuminated a vast construction site. Everywhere within the disk, the first steps of planetary formation were quietly beginning. Small fragments of dust, nearly invisible on their own, were preparing to build some of the most remarkable objects in the solar system. The age of planets was about to begin. The disk formed naturally as the solar nebula collapsed. The original cloud had possessed a slight rotation, almost imperceptible at first. As gravity pulled the cloud inward, this rotation became faster and more significant. Material could no longer fall directly toward the center from every direction. Instead, much of it settled into a broad, flattened disk orbiting the young sun. What emerged was a structure resembling a giant cosmic record, spinning through space while carrying nearly all the remaining material that had not become part of the sun itself. The scale of this disk was enormous. It stretched far beyond the orbit of the modern planets. Its outer edges reached regions that today are occupied by icy bodies and distant remnants of the solar system's early history. Yet despite its immense size, the disk was surprisingly thin compared to its width. If viewed from far away, it would have looked like a delicate glowing ring surrounding the young star. Inside the disk, conditions varied dramatically depending on location. The inner regions were hot, bright, and energetic. Temperatures near the young sun were high enough to melt rock and vaporize many substances. Farther away, conditions became cooler. In the outer regions, ice could survive. Beyond a certain distance, frozen water became abundant, dramatically increasing the amount of solid material available for future planet formation. This boundary played a crucial role in shaping the solar system. Astronomers often refer to it as the snow line. Inside the snow line, water existed primarily as vapor. Outside the snow line, water could freeze into ice. Since water was one of the most abundant compounds in the disk, the ability of ice to survive greatly increased the supply of solid building material. This difference would eventually help explain why small rocky planets formed closer to the sun, while giant planets developed farther away. The disk was not calm or motionless. Although it may seem peaceful when imagined from a distance, it was a highly dynamic environment. Gas flowed through it in complex patterns. Dust grains drifted between regions. Magnetic fields twisted through the material. Turbulence created currents and eddies that carried particles from one location to another. The entire structure was constantly evolving. Tiny dust grains floated throughout the disk. These particles were extraordinarily small, often smaller than grains of smoke, yet they represented the foundation upon which everything else would be built. The rocky surfaces of planets, the metallic cores hidden beneath them, and even the materials that would eventually become living organisms, all began as microscopic particles moving through this disk. The particles were not evenly distributed. Some regions contained greater concentrations of dust than others. In certain areas, particles became trapped in local currents and accumulated together. Elsewhere, collisions and turbulence scattered material apart. These variations would later influence where planets formed and how quickly they grew. As the dust grains orbited the sun, they frequently encountered one another. Most collisions were extremely gentle. At these small scales, forces that are insignificant in everyday life became important. Static electricity and molecular attractions could cause particles to stick together after contact. Tiny clumps formed. Those clumps collided with other clumps. Gradually, microscopic grains became slightly larger aggregates. The process sounds simple, but it represented the beginning of planetary construction. Every mountain on Earth, every grain of sand on a beach, and every rocky landscape on Mars can trace its history back to these early interactions between tiny particles within the protoplanetary disk. Meanwhile, the young sun continued influencing its surroundings. Streams of charged particles known as solar winds flowed outward through the disk. These winds pushed on lighter gases and altered the distribution of material. Intense radiation heated certain regions and changed the chemistry of others. The sun was not merely illuminating the disk, it was actively reshaping it. Over time, the disk began to organize itself. Larger particles tended to settle toward the central plane of the disk. Imagine shaking a container filled with dust and sand. Eventually, the heavier particles moved toward the bottom. Something similar happened within the protoplanetary disk. As particles collided and lost energy, they gradually concentrated within a relatively thin layer around the disk's middle. This concentration increased the frequency of collisions. More collisions meant more opportunities for particles to stick together. The process remained incredibly slow by human standards, but on astronomical timescales it was remarkably effective. Over hundreds of thousands of years, and then millions of years, larger and larger structures began to emerge. The protoplanetary disk also contained a record of the solar system's future diversity. The materials available near the sun differed from those farther away. Temperature determined which compounds could exist as solids. Density varied from region to region. Radiation levels changed with distance. Because conditions were not uniform, the worlds that eventually formed would not be uniform either. This is why Mercury became a small rocky planet, while Jupiter grew into a giant world dominated by gas. It is why Earth developed oceans while other worlds remained dry. The differences between planets began not after they formed, But during this early period when their raw materials occupied different regions of the disk, for several million years, the protoplanetary disk served as a vast workshop where gravity, motion, temperature, and time worked together. Nothing in the modern solar system fully captures how strange this environment was. There were no recognizable planets yet, only countless particles orbiting a young star and interacting in ways that slowly transformed chaos into order. Yet within this apparent disorder, a profound process was underway. Dust grains were becoming clumps. Clumps were becoming larger structures. The first true building blocks of planets were beginning to emerge. Across the disk, billions upon billions of tiny particles were taking the earliest steps toward becoming worlds. And the quiet construction of the solar system had truly begun. At first glance, the idea seems almost impossible. How can something as large as Earth begin as microscopic dust floating through space? The answer lies in a process that unfolded gradually over millions of years, driven by countless collisions between tiny particles. No single collision created a planet. Instead, an unimaginable number of small interactions slowly built larger and larger structures. The dust grains within the protoplanetary disk came from many sources. Some consisted of silicate minerals, similar to the rocky materials found on Earth today. Others contained metallic compounds rich in iron and nickel. Farther from the sun, many grains carried frozen layers of water ice and other compounds. Together, these particles formed a vast mixture of materials left behind from the birth of the solar system. Although space is often imagined as empty, the disk contained enormous numbers of these particles. They orbited the sun at different speeds depending on their distance from the center. As a result, collisions occurred constantly. Most impacts were gentle, unlike the dramatic collisions that would occur later during planet formation. These early encounters often happened at relatively low speeds. When two microscopic grains met, several outcomes were possible. Sometimes they bounced apart. Sometimes they shattered into smaller pieces. But under the right conditions, they stuck together. Tiny electrical forces operating at microscopic scales helped hold the particles in contact. Molecules on their surfaces could attract one another. In colder regions, thin icy coatings acted almost like cosmic glue. The first clusters were extremely fragile. If you could somehow hold one in your hand, it would resemble a delicate dust bunny more than a solid rock. Large empty spaces existed between the particles. The structures were porous and fluffy, yet they represented an important step. For the first time, material within the disk was becoming organized into larger units. As these clumps drifted through the disk, they encountered other clumps. Some merged, others broke apart. Growth was not smooth or guaranteed. Many structures formed only to be destroyed later. But across millions of years, the overall trend favored gradual enlargement. Tiny grains became aggregates. Aggregates became pebbles. Pebbles continued accumulating additional material. One reason this growth was possible is that larger particles interacted differently with the gas surrounding them. The protoplanetary disk was not composed solely of dust. Gas remained abundant, especially hydrogen and helium. As particles moved through this gaseous environment, they experienced drag. Much like air resistance affects objects moving through Earth's atmosphere, gas resistance influenced the motions of particles within the disk. This drag created complex behaviors. Some particles drifted inward toward the sun. Others migrated more slowly. In certain regions, particles became concentrated together, increasing the likelihood of collisions. These local accumulations may have played a crucial role in helping larger structures form. Imagine standing beside a river. Small leaves floating on the water often gather in quiet corners where currents slow down. Similarly, particles within the protoplanetary disk sometimes collected in regions where gas flows created favorable conditions. These concentrations allowed material to build up more efficiently than it could in a perfectly uniform environment. As particles grew from microscopic sizes to pebble-sized objects, gravity still played only a minor role. Their masses remained far too small to exert significant gravitational attraction. Instead, physical contact and microscopic forces dominated the process. Yet every increase in size brought the system closer to a point where gravity would eventually become important. The transition from dust to pebbles represented one of the most challenging stages in planetary formation. Modern scientists continue studying exactly how this process occurred, because it involved many competing effects. Some collisions promoted growth, others caused fragmentation. Gas drag sometimes helped particles gather together but could also pull them toward the sun. The environment was complex and constantly changing. Nevertheless, evidence from observations of young star systems suggests that nature solves this problem remarkably well. Throughout the galaxy, astronomers observe protoplanetary disks surrounding newborn stars. Many display signs that dust grains are growing and evolving. Some contain structures that appear to be the early stages of planet formation. These observations suggest that the processes that shaped our solar system may be common throughout the universe. As millions of years passed, certain regions of the disk became populated by increasing numbers of pebbles and larger fragments. These objects were still tiny compared to planets, but they marked a significant advance. The building materials of future worlds were no longer merely dust. They were becoming recognizable physical objects capable of participating in more complex interactions. The future Earth was still invisible as a distinct world. Jupiter did not yet exist. Mars, Venus, and Saturn were nowhere to be found. Yet the ingredients that would form them were beginning to organize themselves. Countless pebbles drifted through the disk, colliding and gathering in ever larger collections. The process remained slow, quiet, and largely hidden from view. But its consequences would eventually reshape the entire solar system. If someone could observe the disk over millions of years in a cosmic time-lapse, they would witness a subtle transformation. The once uniform haze of dust would gradually become populated with larger structures. Regions of concentration would appear. Material would gather into streams and clusters. The first true seeds of planets would be taking shape. These growing collections of pebbles represented a turning point in the history of the solar system. Gravity had created the sun and the disk. Microscopic forces had transformed dust into larger particles. Now the stage was being set for a new phase of evolution, one in which gravity would begin to act on increasingly massive objects. The era of tiny dust grains was slowly coming to an end, and the first substantial building blocks of future planets were emerging from the swirling disk around the young sun. For many years, scientists struggled to understand how nature crossed this gap. Growing from dust to pebbles was difficult enough, but growing from pebbles to objects hundreds of kilometers wide seemed even more challenging. Simple collisions alone appeared too slow. Many impacts caused fragmentation rather than growth. Some pebbles spiraled inward toward the sun before they could become larger. Yet somehow, the solar system succeeded. Within a relatively short period of cosmic time, the first major building blocks of planets began to appear. These objects are known as planetesimals. A planetesimal can be thought of as a miniature world. Unlike dust grains or pebbles, a planetesimal possesses enough mass for gravity to begin influencing its surroundings. It may be only a few kilometers across, or perhaps hundreds of kilometers wide, but it represents something fundamentally different from the particles that came before it. Once planetesimals formed, the process of building planets became far more efficient. One possibility is that large numbers of pebbles gathered together in concentrated regions of the disk. Instead of growing one collision at a time, entire swarms of particles may have collapsed under their collective gravity. Imagine a dense cloud of snowflakes suddenly becoming heavy enough to collapse into a compact snowball. On a much larger scale, something similar may have occurred within the protoplanetary disk. As pebbles accumulated in certain areas, their combined gravity slowly strengthened. Eventually, some clusters became dense enough that gravity pulled them together into solid objects. The result was the rapid formation of planetesimals. In some regions, this process may have produced bodies tens or even hundreds of kilometers across in surprisingly short periods of time. The birth of planetesimals marked a major turning point. For the first time, recognizable worlds existed within the solar system. They were not planets, but they were no longer mere particles. They had shape, mass, and gravity. If an observer could have traveled through the disk during this era, they would have encountered countless rocky and icy objects orbiting the sun in every direction. Many of these early bodies resembled modern asteroids. Their surfaces were irregular and heavily cratered. Some contained large amounts of metal. Others were rich in rock. Farther from the sun, many incorporated significant quantities of ice. Each planetesimal preserved a record of the conditions under which it formed. The environment remained crowded. Millions of planetesimals shared the disk, traveling along intersecting paths. Collisions became increasingly common. Unlike the gentle impacts between dust grains, these encounters could be dramatic. Some collisions shattered bodies into fragments. Others merged two objects into one larger object. The outcome depended on speed, angle, and composition. Gravity now played a central role. Larger planetesimals exerted stronger gravitational attraction, allowing them to pull nearby material toward themselves. This created a powerful feedback process. The bigger an object became, the easier it became to grow even larger. A planetesimal with twice the mass of its neighbor could attract material more effectively, increasing its growth rate and widening the difference between them. This process is sometimes called runaway growth, because the largest objects begin growing faster than smaller ones. In certain regions of the disk, a few bodies gained an advantage and expanded rapidly. Their gravity altered the motions of nearby planetesimals. Smaller objects were pulled into collisions that added more mass to the growing bodies. The solar system during this period was far from peaceful. Although today's planetary orbits appear orderly and stable, the young disk was a chaotic environment filled with countless collisions. Objects frequently changed trajectories after impacts. Fragments were scattered across space. New bodies formed while others were destroyed. Construction and destruction occurred simultaneously throughout the disk. Closer to the sun, rocky planetesimals dominated. Temperatures remained too high for most ices to survive. These regions contained abundant silicate minerals and metallic compounds. Here, the seeds of Mercury, Venus, Earth, and Mars were beginning to emerge. Farther from the sun, conditions were different. Water, ice, and other frozen materials remained stable. This increased the amount of solid matter available for growth. As a result, planetesimals in the outer solar system often grew larger more quickly. These regions would eventually give rise to the giant planets, whose immense masses would shape the future architecture of the solar system. Some planetesimals grew large enough that their interiors began changing. Radioactive elements trapped within them produced heat. Collisions added additional energy. In certain cases, temperatures became high enough for partial melting to occur. Dense materials such as iron sank toward the center, while lighter materials rose toward the surface. Even before planets existed, some planetesimals were already developing internal structures. Many of the meteorites that reach Earth today are fragments of these ancient bodies. They serve as time capsules from the earliest days of the solar system. By studying them, scientists gain insight into conditions that existed more than 4.5 billion years ago. These meteorites preserve clues about temperatures, compositions, and processes that operated during the era of planetesimal formation. As millions of years passed, the number of planetesimals continued increasing. Some remained small and relatively unchanged. Others participated in repeated mergers that steadily increased their size. The largest bodies became dominant gravitational players within their local regions of the disk. The future planets were still absent. Earth had not yet formed. Jupiter was only beginning its growth. No familiar worlds existed. Yet, the foundations were now firmly in place. The disk contained countless planetesimals, each serving as a potential building block for something larger. Gravity was beginning to sort winners from losers. Some objects would remain small relics of the solar system's youth. Others would continue growing until they became planetary embryos, bodies large enough to begin resembling true planets. The age of dust had passed. The age of pebbles was ending. Across the protoplanetary disk, miniature worlds were colliding, merging, and evolving. From this vast population of planetesimals, the first planetary ancestors were beginning to emerge, setting the stage for one of the most dramatic periods in the history of the solar system. Although the modern solar system appears calm and orderly, its early history was anything but peaceful. The region around the young sun resembled a vast construction zone filled with moving objects. Every planetesimal followed its own orbit. Some traveled in nearly circular paths, while others moved along more elongated trajectories. As these objects crossed one another's paths, collisions became inevitable. Many impacts were relatively gentle. Two bodies would meet and merge, creating a larger object. These mergers were essential because they allowed planetesimals to continue growing. Each successful collision added more mass, increasing the gravitational pull of the newly formed body. Over time, larger objects gained an advantage. Their stronger gravity allowed them to attract nearby material more efficiently, causing them to grow even faster. Not every collision ended peacefully. Some impacts occurred at tremendous speeds. Instead of merging, the objects shattered. Fragments were blasted into space, creating clouds of debris that spread throughout the disk. For millions of years, destruction and creation happened simultaneously. While some bodies grew larger, others were broken apart and recycled into new generations of planetesimals. Gradually, a small number of objects began separating themselves from the crowd. Through repeated mergers, they became much larger than their neighbors. These growing worlds are often called planetary embryos. They were not yet full planets, but they represented an important intermediate stage. Some reached sizes comparable to modern moons. Others became even larger. If you could have observed the inner solar system during this period, you would not have seen 4 rocky planets. Instead, you would have witnessed dozens of planetary embryos sharing the region around the sun. They orbited through a chaotic environment filled with smaller planetesimals and debris. Their gravitational influence constantly disturbed nearby objects, altering orbits and triggering new collisions. The outer solar system experienced similar processes, though conditions there were somewhat different. Because temperatures were lower, ice remained abundant. This provided much more solid material for growth. As a result, planetary embryos in the outer regions often accumulated mass more quickly. These distant bodies would eventually become the foundations of the giant planets. Gravity increasingly shaped everything. Large embryos acted like cosmic magnets, pulling nearby material toward themselves. Smaller planetesimals were captured, absorbed, or thrown into new orbits. The larger a body became, the more effectively it dominated its surroundings. Entire regions of the disk gradually came under the influence of these growing worlds. The solar system at this stage was remarkably crowded. Objects frequently passed near one another. Some encounters were harmless. Others dramatically changed the trajectories of both bodies involved. A close gravitational encounter could send a planetesimal spiraling inward toward the sun, or fling it outward into distant regions of space. The architecture of the future solar system was still far from settled. As planetary embryos grew, their interiors also began changing. The energy released by impacts generated heat. Radioactive elements trapped inside contributed additional warmth. Some embryos became hot enough for their interiors to partially melt. Dense metals sank toward their centers, while lighter materials rose upward. Even before becoming planets, These bodies were beginning to develop layered structures similar to those found inside modern worlds. Among the countless collisions occurring during this era were impacts powerful enough to reshape entire objects. Mountains were erased before they could fully form. Surface layers were stripped away. New material was mixed into old material. Every planetary embryo carried the scars of repeated encounters. Yet despite the violence, a clear trend was emerging. The number of bodies slowly decreased, while their average size increased. Thousands of small objects were gradually being transformed into a smaller population of much larger worlds. The solar system was organizing itself through gravity and collision, slowly moving toward a more stable arrangement. The future Earth was one of these growing embryos. So were the future Venus, Mars, and Mercury. They did not yet resemble the planets we know today, but their foundations were taking shape. Each collision added new material. Each merger increased their mass. With every passing million years, these embryonic worlds moved closer to becoming true planets. The violent age of planet building was one of the most important chapters in solar system history. It was an era when worlds competed for material, when gravity determined winners and losers, and when countless impacts gradually transformed a chaotic disk into the beginnings of a planetary system. Out of this prolonged period of collisions and growth would emerge the familiar planets that continue orbiting the Sun more than 4.5 billion years later. Unlike the giant planets that would form farther from the Sun, the inner planets developed in a region where temperatures remained relatively high. Water ice could not survive near the young Sun, and many lighter materials existed as gas rather than solid matter. As a result, the building blocks available in this part of the solar system were mostly rock and metal. The planets that formed here would become dense, solid worlds with rocky surfaces and metallic interiors. At first, none of these worlds existed as single objects. Instead, each future planet was represented by multiple planetary embryos, sharing similar regions of space. These embryos repeatedly collided and merged. Every impact increased their size and altered their composition. Growth was not smooth or orderly. A planetary embryo might spend millions of years accumulating mass, only to experience a collision that dramatically changed its structure. Mercury formed closest to the Sun, where conditions were most extreme. The intense heat limited the types of materials that could survive. Mercury ultimately became a small world dominated by metal and rock. Even today, it remains the smallest of the major planets. Its enormous iron core occupies a much larger fraction of the planet than Earth's core does. Scientists still debate exactly why Mercury ended up with such an unusually large metallic interior, but its formation was undoubtedly shaped by the harsh environment near the Sun. Farther outward, Venus was taking shape. In many ways, Venus and Earth began with similar ingredients. Both grew within regions rich in rocky material. Both accumulated substantial mass. Both likely experienced enormous impacts during their formation. Yet despite these similarities, their futures would diverge dramatically. Venus would eventually become a world hidden beneath thick clouds and crushing atmospheric pressure, while Earth would develop oceans and life. At this stage, however, both were still molten young worlds under construction. The future Earth was also growing through a long series of collisions. Every impact delivered new material. Some collisions involved relatively small objects, while others were powerful enough to reshape the entire planet. During this period, Earth was not a blue world with oceans and continents. It was a hot and evolving planetary embryo surrounded by other growing bodies. Its surface may have been partially molten for long periods, glowing under the light of the young Sun. Mars formed farther from the Sun, near the outer edge of the inner solar system. Compared to Earth and Venus, Mars accumulated less material. One reason may be that the region where it formed simply contained fewer building blocks. Another possibility is that gravitational interactions with larger growing worlds limited its growth. Whatever the cause, Mars remained relatively small. It became a planet, but one much less massive than Earth or Venus. As these worlds expanded, their interiors underwent important changes. Frequent impacts generated enormous heat. Radioactive elements trapped within the planets produced additional energy. In many cases, temperatures became high enough to melt large portions of the interior. This allowed heavier materials such as iron and nickel to sink toward the center, while lighter rocky materials floated upward. This process, known as differentiation, helped create the layered structures found inside rocky planets today. Deep beneath Earth's surface lies a metallic core surrounded by a thick mantle of rock. Similar processes occurred inside Venus, Mercury, and Mars. The planets were becoming more complex as they grew. The young inner solar system remained dangerous and unstable. Large impacts continued occurring regularly. Entire landscapes could be erased in a single collision. New craters formed constantly. Clouds of debris filled nearby space. Yet every collision contributed to the ongoing construction of the planets. Over time, the number of planetary embryos decreased. Many merged into larger worlds. Others were ejected from the region entirely or fell into the sun. Gradually, 4 dominant planets emerged from the chaos. Their orbits became more stable. Their identities became clearer. The inner solar system was beginning to resemble the arrangement we know today. Even so, these planets were still far from finished. Their surfaces remained hostile and dynamic. Their atmospheres were only beginning to develop. Their interiors were still hot from the energy of formation. Earth had not yet acquired its moon. Oceans had not yet formed. Calm worlds familiar to us today were still in the distant future. Nevertheless, the foundations had been established. 4 rocky planets now occupied the inner solar system. Each carried a unique combination of size, composition, and history. Though born from the same protoplanetary disk, they were already becoming distinct worlds. Their differences, shaped by location, collisions, and chance, would continue growing over billions of years, creating the diverse planetary family that circles the Sun today. The environment where Jupiter formed was dramatically different from the region where Earth emerged. Temperatures were much lower. Water could exist as ice, and frozen compounds such as methane and ammonia were common. Because ice was abundant, there was far more solid material available than in the warmer inner solar system. This gave Jupiter a tremendous advantage from the very beginning. Like all planets, Jupiter started small. Its origins can be traced back to countless dust grains drifting through the protoplanetary disk. These particles stuck together, forming pebbles. Pebbles became planetesimals, and planetesimals gradually merged into larger bodies. Over millions of years, one growing planetary embryo began accumulating material more rapidly than its neighbors. Its increasing mass strengthened its gravitational pull. More planetesimals were captured. More collisions occurred. Growth accelerated. Eventually, the young Jupiter became massive enough that its gravity began influencing an enormous region around it. Instead of simply collecting nearby rocks and ice, it started attracting huge quantities of gas from the surrounding disk. This was the moment that changed everything. Hydrogen and helium made up most of the material in the protoplanetary disk. These gases were difficult for smaller worlds to hold on to, but Jupiter had grown large enough to capture them in vast amounts. Once this process began, Jupiter expanded rapidly. The more gas it accumulated, the stronger its gravity became. The stronger its gravity became, the more gas it could attract. For a period of time, Jupiter experienced extraordinary growth. It transformed from a large planetary embryo into a true giant planet. Layer upon layer of hydrogen and helium surrounded its original core. The planet's mass increased dramatically, eventually exceeding the combined mass of all the other planets in the solar system. If you could have observed Jupiter during this era, it would not have resembled the striped world seen through modern telescopes. The young planet was still forming, still gathering gas, and still radiating enormous amounts of heat generated by its growth. It was a dynamic and turbulent object, surrounded by streams of material flowing inward from the disk. The formation of Jupiter affected far more than the planet itself. Its immense gravity began reshaping the entire solar system. Nearby planetesimals had their orbits disturbed. Some were pulled inward toward the sun. Others were flung outward into distant regions of space. Areas that might have formed additional planets were altered by Jupiter's growing influence. Many scientists believe Jupiter played a crucial role in determining the final architecture of the solar system. Without Jupiter, the arrangement of planets could have been very different. Mars might have become larger. The asteroid belt might not exist in its current form. The paths followed by countless small objects throughout the solar system would likely have changed dramatically. As Jupiter continued growing, it also developed its own miniature system. Around the giant planet, a disk of gas and dust formed, similar in some ways to the larger disk surrounding the sun. Within this smaller disk, moons began taking shape. The largest of these would eventually become worlds in their own right, some larger than the planet Mercury. The young Jupiter generated tremendous amounts of heat. Deep within the planet, pressure increased as more material accumulated. The atmosphere became thicker and denser. Powerful storms likely raged through the upper layers. Although Jupiter never became a star, it came closer than any planet to resembling one. Had it been dozens of times more massive, nuclear fusion might have ignited in its interior. Yet Jupiter remained a planet, albeit the largest one in the solar system. Its gravity became a stabilizing force that would influence planetary motions for billions of years. Even today, Jupiter acts as one of the dominant gravitational players in our cosmic neighborhood. As the protoplanetary disk slowly evolved, Jupiter's growth eventually began to slow. The supply of available gas decreased. The young sun's radiation and solar wind gradually cleared much of the remaining material from the disk. The era of rapid planetary construction was approaching its end. By this point, Jupiter had already secured its place as the giant of the solar system. It contained more mass than all the other planets combined. Its formation had reshaped nearby regions and altered the destinies of countless smaller objects. What began as a collection of dust grains beyond the snow line had become a colossal world capable of influencing the future of the entire solar system. Jupiter's birth marked one of the most important milestones in planetary formation. The giant planet stood as a reminder of how different conditions could produce dramatically different worlds. While Earth and the other rocky planets formed from stone and metal, Jupiter became something far larger, a vast sphere of hydrogen and helium, whose presence would help shape the history of the solar system for billions of years to come. Not long after Jupiter began its rise to dominance, another giant world was taking shape farther from the sun, in the cold outer regions of the protoplanetary disk, where ice and gas remained plentiful. Saturn was slowly assembling itself from the same raw materials that had helped create Jupiter. Although Saturn would eventually become the second largest planet in the solar system, its story followed a slightly different path. The region where Saturn formed was colder and less crowded than the area around Jupiter. There was still an abundance of ice-rich planetesimals drifting through space, but material was spread across a larger volume. Growth proceeded more slowly. Even so, Saturn possessed an important advantage. By the time it began accumulating large amounts of mass, the outer solar system still contained enough gas and solid material to support the formation of another giant planet. Like Jupiter, Saturn began as a growing planetary embryo. Countless icy planetesimals collided and merged over millions of years. Each collision added more mass. As the young world became larger, its gravity strengthened. More material was pulled inward. More collisions followed. Gradually, Saturn grew from a modest embryo into a massive planetary core. Once this core became large enough, it began attracting enormous quantities of hydrogen and helium from the surrounding disk. Gas that had once drifted freely around the young sun now flowed towards Saturn. The process accelerated as the planet's gravity increased. Layer after layer of gas accumulated, transforming Saturn into a giant world. Yet Saturn never reached Jupiter's size. One reason may be timing. Jupiter formed slightly earlier and had already captured a vast share of the available gas. By the time Saturn entered its most rapid growth phase, the protoplanetary disk was beginning to thin. The young sun was gradually clearing away remaining material through radiation and solar winds. Saturn still became enormous, but it had less raw material available than Jupiter. Despite being smaller, Saturn developed a unique character. Its composition contained a higher proportion of lighter materials, making it less dense than any other planet in the solar system. If an impossibly large ocean existed, Saturn would theoretically float. While such an ocean could never exist in reality, the comparison illustrates just how low Saturn's average density is. The young Saturn was far from the serene world we imagine today. During its formation, it was a turbulent place. Gas streamed into the growing planet. Heat generated by gravitational compression flowed outward. Powerful storms likely churned through its atmosphere. The entire planet radiated energy as it settled into its new form. Around Saturn, a smaller disk of gas and dust also developed. Much like Jupiter's miniature planetary system, this disk became the birthplace of moons. Some of Saturn's future satellites formed directly from material orbiting the giant planet. Others may have been captured or altered through later interactions. Over time, Saturn accumulated an impressive family of moons, many of which remain fascinating worlds today. As Saturn's gravity increased, its influence spread throughout the outer solar system. Nearby planetesimals had their orbits altered. Some were pulled inward toward the giant planet. Others were ejected into distant regions. Small bodies that wandered too close often became part of Saturn itself. Over millions of years, the planet cleared much of the material from its neighborhood. Together, Jupiter and Saturn began acting as powerful architects of the solar system. Their combined gravity affected countless objects. Regions of the disk were reshaped. The movements of smaller bodies became increasingly influenced by these giant planets. Even worlds forming far away could feel their presence. Many scientists believe that Jupiter and Saturn may have migrated slightly during their early history. As they interacted with the gas remaining in the disk, their orbits may have shifted from their original positions. These migrations, though relatively small compared to the size of the solar system, could have influenced the development of other planets and helped determine the final arrangement we see today. As millions of years passed, the era of giant planet formation slowly began drawing to a close. The supply of gas that had fueled their growth was disappearing. The protoplanetary disk was becoming thinner and less capable of producing additional massive worlds. The window of opportunity for creating giant planets was limited, and Saturn had formed just in time. By the end of this period, Saturn had become one of the dominant members of the solar system. Although smaller than Jupiter, it was still a colossal world many times larger than Earth. Its gravity shaped nearby regions. Its growing family of moons orbited around it, and its future ring system was beginning to take shape through processes that would continue for billions of years. From a collection of icy particles drifting beyond the young sun, Saturn had transformed into a giant planet of remarkable beauty and scale. Alongside Jupiter, it stood as evidence that the outer solar system followed a different path from the inner worlds. Here, distance from the sun allowed gas and ice to remain abundant, giving rise to planets far larger than anything that could form closer to the star. Together, these giants were helping define the structure of the solar system that would eventually become our home. Far beyond the orbits of Jupiter and Saturn, the young solar system grew quieter, darker, and far colder. Sunlight was much weaker in these distant regions. The warmth that reached Earth was only a faint memory here. Yet even in this remote frontier, planets were forming. Two worlds, Uranus and Neptune, were slowly emerging from the icy materials scattered across the outer reaches of the protoplanetary disk. The formation of Uranus and Neptune was more difficult than the formation of Jupiter and Saturn. The farther a planet formed from the Sun, the larger the area it had to gather material from. Objects were spread farther apart, and collisions occurred less frequently. Growth was slower. A planet forming in these distant regions had to be patient, collecting material over millions of years while the solar system continued evolving around it. Like the other planets, Uranus and Neptune began as tiny dust grains drifting through the disk. Those grains became pebbles. The pebbles became planetesimals, and the planetesimals gradually merged into larger bodies. Over time, several growing embryos appeared in the outer solar system. Some gained more mass than others, eventually becoming the foundations of Uranus and Neptune. Unlike Jupiter and Saturn, however, these planets never captured enormous amounts of hydrogen and helium. By the time their cores became sufficiently large, much of the gas in the protoplanetary disk had already begun disappearing. The young sun was steadily blowing away the remaining material. As a result, Uranus and Neptune missed the opportunity to become giant gas planets. Instead, they developed into what are often called ice giants. Their interiors contained large amounts of water, methane, ammonia, and other frozen compounds that had been abundant in the cold outer solar system. Deep inside these worlds, pressures became so extreme that these materials no longer behaved like ordinary ice. They existed in unusual states unlike anything commonly experienced on Earth. Although smaller than Jupiter and Saturn, Uranus and Neptune were still enormous worlds. Each contained many times the mass of Earth. Their thick atmospheres, deep interiors, and powerful gravity made them major planets in their own right. Yet because they formed in such distant regions, they remained very different from both the rocky planets and the gas giants. As they grew, Uranus and Neptune influenced their surroundings just as the other giant planets had. Their gravity altered the paths of countless smaller bodies. Some icy planetesimals were absorbed into the growing planets. Others were scattered into distant regions of the solar system. These interactions helped shape the populations of comets and small icy worlds that still exist today. One of the most unusual events in planetary history may have occurred during the formation of Uranus. At some point, the young planet appears to have experienced a massive collision. Today, Uranus rotates on its side, with its axis tilted by about 98 degrees. Unlike the other planets, it essentially rolls around the sun rather than spinning upright. Many scientists suspect that a gigantic impact during its youth knocked the planet into this strange orientation. If this collision occurred, it would have been one of the most dramatic events in the early solar system. A world perhaps several times larger than Earth may have slammed into Uranus, permanently altering its rotation. The scars of that ancient encounter remain visible billions of years later. Neptune followed a somewhat different path. Although slightly smaller than Uranus in diameter, it contains more mass and possesses stronger gravity. Neptune eventually became the outermost major planet of the solar system. Its influence extended deep into the distant regions beyond its orbit, affecting countless icy bodies that orbited even farther from the sun. The space surrounding these planets was becoming increasingly empty as the protoplanetary disk disappeared. Gas that had once filled the solar system was fading away. Dust concentrations diminished. The era of major planetary growth was ending. Uranus and Neptune were among the last large planets to complete their formation before the raw materials of the disk vanished. Even after their growth slowed, both planets remained active worlds. Deep internal heat drove weather systems through their atmospheres. Powerful winds swept across their cloud tops. Methane in their upper atmospheres gave them their beautiful blue color, distinguishing them from the larger gas giants closer to the sun. By this stage, the solar system was beginning to resemble the arrangement we recognize today. 4 rocky planets occupied the inner region. Jupiter and Saturn dominated the middle distances. Uranus and Neptune orbited in the far outer reaches. The major planets had largely claimed their positions. Yet the story was not complete. Vast numbers of smaller objects still remained scattered throughout the solar system. Asteroids, comets, and icy planetesimals continued orbiting the Sun. Some would survive largely unchanged for billions of years. Others would participate in future collisions and migrations that continued shaping the solar system long after the planets themselves had formed. Uranus and Neptune stood at the edge of a growing planetary family, marking the boundary between the major planets and the distant frontier beyond. Their formation demonstrated how location could influence destiny. Had they formed closer to the Sun, they might have become entirely different worlds. Instead, they emerged as icy giants, silent blue guardians of the outer solar system, orbiting in regions where sunlight was faint and the night between the stars seemed almost endless. As the planets slowly took shape around the young Sun, they were not forming alone. Throughout the solar system, smaller companions were also beginning to appear. These companions would become moons, worlds that orbit planets rather than stars. Some would remain small and irregular, little more than captured rocks drifting through space. Others would grow into remarkable worlds with mountains, valleys, oceans hidden beneath ice, and landscapes every bit as fascinating as those of the planets they orbit. Today, the solar system contains hundreds of known moons. Some are larger than entire planets. Others are tiny objects only a few kilometers across. Despite their differences, most moons can trace their origins back to the same chaotic period when the planets themselves were forming. The giant planets were especially important in moon formation. As Jupiter, Saturn, Uranus, and Neptune grew larger, they became surrounded by disks of gas and dust. These smaller disks resembled miniature versions of the protoplanetary disk that had formed around the Sun. Within them, particles collided, merged, and gradually accumulated into moons. Around Jupiter, this process produced some of the largest moons in the solar system. 4 of them became especially prominent. They formed from the material orbiting the giant planet, while Jupiter itself was still growing. Each developed its own unique characteristics. Some became icy worlds. Others became rocky. One would eventually become the most volcanically active body in the entire solar system. Saturn experienced a similar process. Its growing disk of material produced a large family of moons. Over time, these moons settled into stable orbits around the giant planet. Some remained relatively small, while others became major worlds. One of Saturn's moons would eventually develop a thick atmosphere, making it one of the most intriguing places in the solar system. The farther giant planets, Uranus and Neptune, also acquired their own collections of moons. Although these planets formed in more distant and less crowded regions, they still gathered companions through a combination of local formation and gravitational capture. Their moon systems became smaller than those of Jupiter and Saturn, but they remained diverse and fascinating. Not every moon formed from a disk around a planet. Some were captured during the early solar system. Countless planetesimals and smaller bodies traveled through space. Occasionally, a passing object would lose enough energy to become trapped by a planet's gravity. Instead of continuing around the Sun, it would begin orbiting the planet. Many irregular moons likely formed this way. Captured moons often have unusual orbits. Some travel far from their parent planets. Others move in directions opposite to the planet's rotation. These odd paths provide clues that they may have originated elsewhere before being captured long ago. The rocky planets also acquired moons, though through different processes. Mercury ended up without any moon at all. Venus shares the same fate today. Mars possesses 2 small moons that may be captured asteroids or remnants of ancient collisions. Earth, however, followed a very different path. At that stage of the story, Earth did not yet have the moon we see in the night sky today. The event that would create it had not yet occurred. Earth was still a young and evolving planet, surrounded by debris left over from its formation. One of the most dramatic collisions in solar system history was still waiting to happen. While the planets continued settling into their orbits, moons were becoming an increasingly important part of the solar system. Some helped stabilize planetary rotations. Others influenced tides, orbital dynamics, and the movement of nearby material. Though smaller than planets, moons played significant roles in shaping their environments. Many of these moons remained geologically active for long periods. Internal heat, generated by their formation, radioactive materials, and gravitational interactions kept some of them surprisingly dynamic. Volcanoes erupted, ice cracked and shifted, subsurface oceans formed. What began as simple collections of rock and ice gradually evolved into complex worlds. If you could travel through the young solar system during this era, you would see planets accompanied by growing families of satellites. Around the giant planets, miniature systems resembling tiny solar systems were taking shape. Around the rocky planets, smaller companions orbited or awaited their eventual creation. The solar system was becoming richer and more diverse with every passing million years. The formation of moons demonstrated that planetary construction was not limited to the planets themselves. Everywhere gravity operated, it encouraged matter to gather into larger structures. Worlds formed around worlds. Systems developed within systems. The same forces that built the planets were creating entire populations of smaller bodies alongside them. By the time the major planets finished forming, many of their moons had already established themselves as permanent members of the solar system. Some would remain largely unchanged for billions of years. Others would continue evolving long after their birth. Together, they added another layer of complexity to an already remarkable planetary family, transforming the solar system into a collection not only of planets, but of countless smaller worlds with stories of their own. Between the orbits of Mars and Jupiter lies a region that has fascinated astronomers for centuries. Today it is known as the asteroid belt, a vast collection of rocky objects orbiting the Sun. At first glance, it might seem like a place where a planet failed to form, a cosmic construction site abandoned before the job was finished. In some ways, that description is surprisingly close to the truth. When the solar system was young, the region between Mars and Jupiter contained plenty of material. Dust grains, pebbles, and planetesimals filled the area just as they did elsewhere in the protoplanetary disk. Under different circumstances, these building blocks might have merged into another rocky planet. The ingredients were certainly available, yet something prevented that outcome. The answer largely involves Jupiter. As Jupiter grew into the largest planet in the solar system, its gravitational influence spread across enormous distances. Even objects hundreds of millions of kilometers away felt its pull. The region between Mars and Jupiter became strongly affected by the giant planet's presence. Instead of allowing planetesimals to settle into stable growth patterns, Jupiter continually disturbed their orbits. Imagine trying to build a sandcastle while someone repeatedly shakes the ground beneath you. The materials are there, but every attempt to create something larger is disrupted. A similar situation occurred within the future asteroid belt. Planetary embryos and planetesimals frequently had their paths altered by Jupiter's gravity. Collisions became more energetic and destructive. Objects that might otherwise have merged were often shattered apart instead. Over millions of years, countless impacts occurred throughout the region. Some bodies grew for a time before being broken apart. Others survived largely intact. The overall result was that no single object managed to gather enough material to become a full-sized planet. The asteroid belt remained a population of smaller worlds rather than a single dominant one. Today, many people imagine the asteroid belt as a crowded field of rocks packed closely together. Science fiction often portrays spacecraft weaving through dense swarms of asteroids. The reality is much quieter. Although the belt contains millions of objects, The distances between them are enormous. A spacecraft could pass through the asteroid belt without ever coming close to another asteroid. The largest object in the belt is a body known as Ceres. Discovered in 1801, it contains a significant fraction of the belt's total mass. Ceres is large enough for its own gravity to pull it into a roughly spherical shape, earning it the classification of a dwarf planet. If the asteroid belt had experienced a different history, bodies like Ceres might have continued growing into something much larger. Alongside Ceres are many other notable asteroids. Some are rocky, some contain large amounts of metal. Others preserve ancient materials dating back to the earliest days of the solar system. These objects are among the oldest surviving relics from the era of planetary formation. Unlike planets, which underwent extensive geological evolution, many asteroids remain relatively unchanged. In this sense, the asteroid belt functions like a museum of solar system history. The objects within it preserve clues about conditions that existed more than 4.5 billion years ago. By studying asteroids, scientists can learn about the composition of the early protoplanetary disk and the processes that shaped the planets. Not all asteroids are the same. Some form closer to the sun and are rich in rocky minerals. Others contain darker materials and significant amounts of carbon compounds. Certain asteroids even show evidence of ancient water locked within minerals. These differences reveal that the early solar system was chemically diverse, with different regions producing different kinds of building blocks. Collisions continued shaping the asteroid belt long after its formation. Large impacts shattered some asteroids into families of smaller fragments. These families still exist today, groups of objects sharing similar orbits because they originated from a common parent body. Every crater, every broken fragment, tells part of a story stretching back billions of years. Occasionally, asteroids are nudged out of the belt. Gravitational interactions with Jupiter and other planets can alter their paths, sending them into different regions of the solar system. Some eventually cross Earth's orbit. A few have even struck our planet over the course of its history. While these impacts can be dramatic, they also remind us that the asteroid belt remains connected to the wider solar system. The asteroid belt is often described as leftover material from planet formation, but that phrase can be misleading. These objects are not merely scraps. They are survivors. They endured the chaotic era of planetary construction, avoiding incorporation into larger worlds while preserving a record of the solar system's earliest history. As the major planets settled into their orbits, the asteroid belt remained as a reminder of a time when the solar system was still under construction. It marked a boundary between the rocky inner planets and the giant worlds beyond. Within this region, countless ancient bodies continued circling the sun, carrying with them memories of an age when planets were still being born and the architecture of the solar system had not yet fully taken shape. While the planets were forming and the asteroid belt was taking shape, countless smaller objects were being pushed toward the distant outskirts of the solar system. Far beyond the warm regions where the rocky planets formed, temperatures were so low that water, carbon dioxide, methane, and ammonia could remain frozen for billions of years. In these remote and icy realms, comets were born. Today, comets are among the most beautiful objects visible in the night sky. Their glowing tails can stretch across millions of kilometers, creating spectacular displays that have fascinated humans throughout history. Ancient civilizations often viewed comets as omens or messages from the heavens. In reality, they are ancient survivors from the earliest days of the solar system, preserving material that has remained largely unchanged since the era of planet formation. A comet begins as a relatively small object composed of ice, dust, rock, and frozen gases. Unlike asteroids, which are mostly rocky or metallic, comets contain large amounts of frozen material. In many ways, they are cosmic deep freezes, preserving ingredients from the young solar system exactly as they existed billions of years ago. During the formation of the giant planets, especially Jupiter and Saturn, enormous gravitational disturbances swept through the outer solar system. Countless icy planetesimals had their orbits altered. Some were thrown inward toward the sun. Others were ejected completely from the regions where they formed. Instead of becoming part of planets, these objects were scattered into distant reservoirs where many remain today. The early solar system was far more crowded than it is now. Beyond the giant planets existed vast populations of icy bodies. Some collided and merged. Others drifted through space largely undisturbed. Over time, many found stable homes in the outermost reaches of the sun's gravitational influence. There, far from the warmth of the sun, these objects remained frozen. Temperatures dropped to levels almost impossible to imagine. Sunlight became weak and distant. A comet orbiting in these regions could spend millions of years in complete darkness, moving silently through space with little change to its appearance. For most of their existence, comets are inactive. They do not possess bright tails or glowing clouds. They simply appear as dark, icy objects. In fact, many comets are surprisingly black, reflecting only a small fraction of the sunlight that reaches them. Their spectacular appearance emerges only when they travel closer to the sun. As a comet approaches the inner solar system, solar heat begins warming its surface. Frozen gases start turning directly into vapor. Jets of gas erupt from the comet, carrying dust particles into space. A glowing cloud forms around the nucleus, and solar radiation pushes material outward, creating the familiar tail. One of the most remarkable features of a comet is that its tail always points away from the sun. This is not because the comet is moving in that direction, but because sunlight and solar wind continuously push the released material outward. As a result, a comet can appear to drag an enormous luminous tail behind it as it races through space. Some comets visit the inner solar system frequently. Others may take thousands or even millions of years to complete a single orbit. A few make one journey toward the sun and never return, either because they break apart or because gravitational interactions send them into interstellar space. Scientists are especially interested in comets because they contain primitive materials from the birth of the solar system. By studying them, researchers gain valuable insights into the environment that existed before the planets fully formed. Some comets even contain organic molecules, the carbon-based compounds associated with the chemistry of life. There is also evidence that comets may have helped shape the early Earth. During the chaotic period following planetary formation, impacts were common throughout the solar system. Some scientists believe that comets delivered portions of Earth's water and organic materials. While the exact contribution remains debated, it is clear that these icy visitors played an important role in the broader history of the solar system. The giant planets continued influencing comets long after their formation. Jupiter, in particular, acts as a powerful gravitational gatekeeper. Some comets are captured into shorter orbits because of Jupiter's influence. Others are ejected entirely from the solar system. Even today, the giant planets help determine the paths followed by many icy bodies. If you could stand on a comet during its long journey through the outer solar system, the view would be extraordinarily quiet. The sun would appear as a bright star rather than a blazing disk. The planets would be invisible or barely detectable. Everything would seem frozen in time. Yet hidden within that small icy world would be material older than Earth itself, preserved from an era when the solar system was still under construction. Comets are more than wandering objects with beautiful tales. They are ancient messengers from the dawn of the solar system. Each one carries fragments of a story that began more than 4.5 billion years ago. As they travel between the distant frontier and the inner planetary region, they connect the modern solar system to its earliest history, reminding us that even the smallest icy body can preserve the memory of an ancient cosmic past.
you.